Hello there. Let's talk about a type of self-balancing binary search tree called an AVL tree. Okay, so by now I hope you've seen my other videos that I've posted previously where we talked about binary search trees, how to define them, terminology, how to know you're actually looking at one, how to build them, insert, remove, modify, all that stuff, time complexity. If you finished those videos already with me, then you know that binary search trees can actually get slow sometimes because if we have bad data, regular binary search trees don't really know how to rearrange themselves. They just might become slow depending on how good or bad the data is. If the data is totally random, then on average, the trees will be log time, but that's not always the case. Maybe sometimes you have bad data, sorted data, poisoned data, whatever kind of data. So the secret to AVL trees is we're going to start with a binary search tree. And so first it has to satisfy all the rules of a binary search tree, and then we add on another rule. The rule is going to be that we don't have a valid AVL tree if the balance factor for any of the nodes, we'll talk about balance factors in a second, if the balance factor for any node is 2 or worse. Meaning if we think the tree is too imbalanced at any node, it's not a valid AVL tree, and therefore we must rebalance the tree with something called a rotation. After we do enough rotations and we see that the tree is balanced again, then it'll be valid. And so AVL trees sometimes are invalid in some intermediate state. Like if you have an AVL tree and you add some data into it, for a moment it might be an invalid AVL tree, and then internally it's sort of just like rotating itself and rebalancing itself. Then when the tree is done, you'll have a valid AVL tree again, if that makes sense. So suppose this tree here, we can tell this is a valid binary search tree because it follows all the rules that we talked about before. So let's start implementing the first rule of an AVL tree, which is let's compute the balance factors for every single node. How do we compute balance factors? The basic idea is, I want to say BF for balance factor is going to be the absolute value of the difference of the left subtree height minus the right subtree height. If you don't know what a subtree or a height is, you should probably check out my other videos right now. But basically, we're just going to take the absolute value just to get the difference in the height of the left and the height of the right. So if you know binary search trees already, then you know that the leaves, they don't have any subtrees. So their balance factor is going to be pretty easy to compute. It's just going to be a 0. I should also point out that some other tutorials out there use positive and negative numbers for the balance factor. That's okay. I'm just going to use absolute values here because it's a little bit more simple. So all the leaves get a balance factor of 0, which is fine. We're looking to see if we can find a balance factor of 2 or worse to indicate to us that we have an invalid AVL tree. So far, so good. Let's look at the 22 node. So for the 22 node, we'll compute the height of the left subtree versus the height of the right subtree. So I'm going to highlight its left subtree. That's just the 14 node that has a height of 1. And then its right subtree is just the 36 node that also has a height of 1, which means the balance factor for the 22 node is the absolute value of 1 minus 1 is 0. So actually the 22 node is perfectly balanced. If you think about it, that makes sense. Left and right subtrees have the same height. No problem. So I'm going to move on. Let's compute the balance factor for the 48 node. This is a little trickier. Notice how the right subtree has a height of 1 and there is no left subtree, which means its height is 0. So for the 48 node, it's actually going to be the absolute value of 0 minus 1, or just 1. So we find our first node that's a little bit out of whack. It's a little bit of an imbalance here. But AVL trees tolerate imbalances of 1. They don't really care. We sort of try to make a trade-off between constantly always rotating every single time anything happens, which would perhaps burn a little too much CPU, versus letting the tree just be imbalanced to a reasonable amount so we could still call this a log tree in the end. So we consider this to be okay. So far, this is a valid AVL tree. Let's go up to the 65 node and compute the balance factor. So 65 node has no right subtree, so the height is 0 there. And its left subtree is those two nodes on the left, so that has a height of 2, which means the balance factor for the 65 node is going to be the absolute value of 2 minus 0 is to, at this point, we are already certain that this is not a valid AVL tree, and it would need to be rebalanced or rotated before we could, consider it a valid AVL tree in the future. So invalid AVL tree, still a valid binary search tree. Something has to be done. Normally what I would say is if you find some nodes way down lower in the tree that are imbalanced, then just go ahead and perform a rebalancing or a rotation immediately, because sometimes when you rotate lower in the tree, you'll end up fixing nodes that are a little higher. But since we started with this tree and we're not kind of building a tree step by step, I just want to compute the balance factor for all of the nodes at the same time. So we'll do the same thing for the 41 node, the root node. Its left subtree has a height of 2, and its right subtree has a height of 3. So its balance factor is the absolute value of 2 minus 3 is 1. So actually the root node is okay. If it was only up to the root node, we would say this is a valid AVL tree and we don't really need to do anything. However, we've already seen that the 65 node is invalid. So again, we need to do something. Here's another quick example before we move on to actually identifying which nodes to modify and rotate. Just real fast, I want to show you. You know that a binary search tree could actually end up being a linear tree if you had really, really, really bad data. The binary search trees don't self-balance, so it could get this bad. This is slow because this is a linear tree. The time complexity of searching through this tree is linear time. It scales linearly with the number of nodes in your data set. That's really far away from log time, which is supposed to be lightning fast. So an AVL tree will fix this kind of bad data. Let's take a step back here and focus your attention for a second on these 3 nodes. We noticed that there is one node that's actually out of whack. It's the 65 node, right? What we're going to do is we're going to find a trinode subtree that starts with the first node or the lowest node we can find that's out of whack. It's the 65 node, and you can tell that if we just kind of go down a level and down another level to select the other 2 nodes, it's just going to be this little, subtree of 3 nodes, or otherwise known as a trinode subtree. So here's kind of a diagram for that. Whoops, forgot to delete that earlier. Let me get rid of that. So this is the trinode subtree that we selected, right? So we've got the 65 and the 48 and the 55. How did we actually select this? So what you kind of want to do is the first node that is out of whack, you want to call that Z. So I'm going to write a Z here. What we're looking for is a trinode subtree, which we'll first call X and Y and Z. And then we'll end up reordering the nodes and then rearranging all the pointers to the nodes so that the trinode subtree is a little bit more imbalanced. So we see the Z node. We have to find the Y node next. To find the Y node, what's going on with my computer? Oh, there we go. We have the Z node. To find the Y node, really we're just going to take the child of the 65 node that has the taller subtree. So there's only one subtree, on the left. There's no subtree on the right of the 65 node. So the choice is obvious. But just so you know, if there was, another, child hanging off of the right for some reason, we would still choose the number 48 node as the Y node because it has the taller subtree. Notice how the subtree on the left is 2 and the subtree on the right has a height of 1. So always take the taller subtree when you're looking for Y and then X. So then we do the same thing. We go down to the grandchild of the Z node. And if we had a choice to go left or right, again, we would always choose the taller subtree. In this case, there's only one choice. So that X node is going to be the 55. Now in this next slide, I've kind of redrawn this in a little bit different of a way. Notice the trinode subtree that we just selected here, the 65, 48, 55 subtree. It has a height of 3. That should be obvious, right? It's just got a height of 3. We could redraw this subtree in a way that has a shorter height. Notice on the left, these are the same 3 nodes. Exactly, 48, 55, and 65. That's the same 3 nodes that we originally had. But notice how the height is 2. So the basic idea for AVL trees is, compute the balance factors, and as soon as you identify a node that's out of whack, you grab a trinode subtree starting at the node that's out of whack, the Z node, and then we'll perform quote-unquote a rotation where we just kind of smush it to be a little bit more balanced and a little bit shorter. So the height goes from 3 to 2. Once we do that, the rest of the tree is going to get a little bit better. You'll notice that this will end up sometimes completely, but sometimes partially fixing bad balance factors in the tree. So this is the end of the intro. I only wanted to spend a little time just kind of like warming you up to the idea. In the next videos, we're going to actually look at performing rotations, identifying the 4 different types of rotations that you could see and like how to do them. We'll talk more about the idea that we're really just rearranging pointers here. If you're thinking about code, you're thinking about, oh, I've got some pointers between these nodes. We're not going to delete any nodes or add any nodes. We're just going to like rearrange who is a parent of who is a child of who. And then eventually we'll deal with some really bad trees and we'll become experts at just like maintaining AVL trees. And we'll talk about ways to visualize the rotations, which makes it a little bit easier to remember these patterns and stuff. Okay, so thank you for watching this video. I hope you learned a little bit of stuff and had a little bit of fun. In the next one, we're gonna get started. We're gonna go deep. I'm gonna get my gear. Sorry. Hey everybody. Thanks for watching this video again. From the bottom of my heart, I really appreciate it. I do hope you did learn something and have some fun. If you could do me a small little favor, could you please subscribe and follow this channel or these videos or whatever it is you do on the current social media website that you're looking at right now. It would really mean the world to me, and it'll help make more videos and grow this community. So we'll be able to do more videos, longer videos, better videos, or just I'll be able to keep making videos in general. So please do me a kindness and subscribe. You know, sometimes I'm sleeping in the middle of the night and I just wake up because I know somebody subscribed or followed. It just wakes me up and I get filled with joy. That's exactly what happens every single time. So you could do it as a nice favor to me, or you could troll me if you want to just wake me up in the middle of the night. Just subscribe and then I'll just wake up. I promise that's what will happen. Also, if you look at the middle of the screen right now, you should see a QR code which you can scan in order to go to the website, which I think is also named somewhere at the bottom of this video. And it'll take you to my main website where you can just kind of like see all the videos I published and the services and tutorials and things that I offer and all that good stuff. And if you have a suggestion for clarifications or errata or just future videos that you want to see, please leave a comment. Or if you just want to say, hey, what's up? What's going on? You know, just send me a comment, whatever. I also wake up for those in the middle of the night. I wake up in a cold sweat and I'm like, it would really mean the world to me. I would really appreciate it. So again, thank you so much for watching this video, and enjoy the cool music as I fade into the darkness, which is coming for us all.